Electricity is everywhere. It flows through the walls, runs beneath streets, and fills the air with invisible structure. It powers homes, hospitals, and entire cities without pause. Every screen lighting up, every motor turning, every signal traveling across the planet depends on it. Life in the modern world would stop within seconds without electricity. And yet, despite how familiar it feels, its true nature remains surprisingly unclear. For over a century, physicists have studied electricity with intense focus. Equations describe it with stunning accuracy. Technologies built on those equations work almost perfectly. Still, when experts try to explain what electricity actually is, the answers begin to shift. Some describe it as moving charges. Others point to electric fields. Some focus on energy flow through space rather than through wires. Each explanation works in certain situations, but none tell the full story. This creates a strange contradiction. Electricity is one of the most useful forces ever harnessed, yet it remains one of the hardest to explain in simple terms. Even professionals often rely on models they know are incomplete. These models are not wrong, but they hide deeper questions that rarely make it into textbooks or classrooms. In this video, you will learn why electricity behaves in ways that seem simple on the surface but become confusing when examined closely. You will discover why electrons move far slower than the electrical effects they create. You will learn how energy can flow through empty space around a wire instead of through the wire itself. These are not fringe ideas. They are established facts that challenge the way electricity is commonly taught. You will also explore why physics uses multiple explanations for the same phenomenon. One model works for circuits, another works for fields, another works at the quantum level. Each is accurate within its limits, yet none can fully replace the others. This layered understanding reveals something important about science itself. Sometimes knowing how to calculate an effect comes long before truly understanding its nature. There are lesser-known details that make this topic even more intriguing. For example, when a light turns on, the energy that lights the bulb does not arrive by electrons traveling from the power plant. That journey would take hours. Instead, the energy moves almost instantly through electric fields already present around the wire. The electrons barely drift at all. This simple fact alone reshapes how electricity should be understood. There were also moments in history where physicists openly disagreed about what electricity really was. Some believed it was a fluid. Others thought it was a vibration of space. Even today, debates continue over how best to describe it without misleading intuition. The mathematics works. The concepts struggle to keep up. As this video continues, you will see how electricity connects to magnetism, how fields carry energy, and why space itself plays a role in electrical behavior. You will learn why common explanations are useful but incomplete, and you will understand why electricity still challenges our intuition, even in an age of advanced science and technology. Watching until the end matters because each idea builds on the last. The early assumptions give way to deeper insight. Simple pictures break down, revealing something more subtle underneath. By the final moments, electricity will no longer feel like just something that flows through wires. It will feel like a structured interaction between matter, space, and energy. Welcome to our channel, where we explore the hidden side of everyday forces and uncover the questions science is still working to answer. If you enjoy deep explanations that challenge simple ideas, subscribe to the channel and stay with us as we continue to break down the mysteries behind the world that powers our lives. Electricity feels simple because it behaves the same way every day. A switch is flipped and the light turns on without delay. A button is pressed and a device responds exactly as expected. This reliability creates comfort. It suggests that electricity is fully understood, controlled, and predictable. When something works perfectly thousands of times, it feels natural to assume that its behavior must also be simple. This sense of simplicity comes from how electricity is used, not from how it actually works. Most interactions with it are reduced to basic actions: on and off, charge and discharge, power flowing or stopping. These outcomes hide the processes happening underneath. The system is designed so users never need to think about what is occurring inside the wires, circuits, or components. The complexity is carefully concealed behind smooth performance.
The instant response of electrical devices is especially misleading. The light turns on so fast that it feels like something moved directly from the switch to the bulb. In reality, different processes are happening at different speeds. Signals spread rapidly. Energy rearranges itself. Charges respond locally rather than traveling across long distances. What looks like a single action is actually a coordinated interaction across space.
The predictability also plays a role. Electrical systems follow strict rules, and those rules rarely fail under normal conditions. This makes electricity seem mechanical, almost like a solid object that can be pushed and pulled. But beneath this order lies a system governed by invisible fields, shifting energy distributions and interactions that cannot be seen or touched. These elements are described by mathematics rather than intuition. As explanations go deeper, familiar ideas begin to lose clarity. Electrons do not behave like tiny balls moving through pipes. Energy does not stay confined inside metal. Space itself becomes part of the system. The deeper reality of electricity is not simple motion or direct flow. It is a layered interaction that only appears simple because its complexity has been hidden behind consistent results. The most common explanation of electricity begins with moving charges. In classrooms and textbooks, electricity is introduced as electrons flowing through wires. A battery pushes these electrons forward. A circuit provides a path. When the electrons move, electrical energy is delivered to a device. This picture is easy to visualize and simple to teach. It gives students something concrete to hold on to. This model works well at a basic level. It explains why a closed circuit is needed for current to flow. It shows why materials like copper conduct electricity while others do not. It helps make sense of concepts like current, resistance, and voltage. For many practical purposes, this explanation is enough. Engineers can design circuits. Technicians can fix systems. Devices can be built and tested reliably. Because of this success, the moving electron model becomes deeply ingrained. It feels intuitive, particles move, energy is carried along with them. The wire acts like a pipe, and electricity behaves like a flowing substance. This mental image is powerful, and it rarely fails in everyday situations. As long as devices work, the explanation feels complete. Problems appear only when the model is pushed too far. Electrons in a wire actually move very slowly. Their average drift speed can be less than a millimeter per second, yet electrical effects travel close to the speed of light. A light turns on almost instantly, even though the electrons that respond are mostly local. This gap between motion and effect reveals a flaw in the simple picture. The classic explanation also struggles to describe where energy actually travels. If electrons move slowly, they cannot be carrying energy across long distances in real time. Something else must be happening. The model still produces correct calculations, but its physical interpretation starts to break down. It remains useful, but it leaves key questions unanswered about how electricity truly operates beneath the surface. The cracks in the classic explanation appear when speed is examined more closely. If electricity was simply electrons traveling through a wire, the response of a circuit would be slow. In reality, electrical signals move extremely fast. When a switch is flipped, the effect reaches the other end of the circuit almost immediately. This happens long before electrons could physically travel any meaningful distance. The motion of electrons and the speed of electrical response clearly do not match. This leads to a deeper question about how energy actually moves. The common image suggests that energy rides along with electrons as they drift through metal. But experiments show that energy reaches devices without waiting for electrons from the power source to arrive. The electrons already present in the wire shift slightly, responding to a change that spreads through the system. Energy flows as a result of this shift, not as a package carried by individual particles. At this point, electric and magnetic fields enter the picture. Fields exist throughout space, even when nothing appears to be moving. When a circuit is completed, these fields reorganize almost instantly. This reorganization guides how energy moves from one place to another. The wire does not deliver energy like a conveyor belt. Instead, it shapes the surrounding fields, which direct energy through space toward the load. This idea is difficult to visualize. Fields are invisible and abstract. They do not behave like solid objects or flowing liquids. They respond to changes everywhere at once, following mathematical rules rather than physical intuition. As a result, even students who master equations often struggle to form a clear mental picture of what is happening. The shift from particles to fields marks a turning point in understanding electricity. The math becomes more reliable, but the story becomes less intuitive. Many learners can calculate outcomes without feeling confident about what electricity truly is, revealing how the familiar explanation begins to fail at deeper levels. Electric and magnetic fields exist even when a system appears still. A charged object creates an electric field around it without any visible motion. A steady current produces a magnetic field that remains in place as long as the current flows. These fields are not side effects. They are fundamental parts of how electricity works. They fill the space around conductors, components, and even empty regions where no material is present. When a circuit is active, Energy does not stay confined inside the metal of a wire. It moves through the surrounding space, guided by the electric and magnetic fields that form around the circuit. This flow of energy can be described precisely using physics, and it shows that most of the energy travels outside the wire rather than within it. The wire plays a different role than many expect. It does not act as a pipeline carrying power from one end to the other. Instead, the wire shapes and constrains the fields. Its geometry and material properties determine how the fields arrange themselves in space. This arrangement directs energy toward devices connected to the circuit. The energy follows paths defined by the fields, passing through the space around the wire and into components where it is converted into light, heat, or motion. The electrons inside the wire respond locally, adjusting to support this process rather than transporting energy across distances.
This perspective changes how electricity is understood at a basic level. Power delivery becomes an interaction between fields and space, not just particles and metal. It explains why changes in a circuit are felt almost instantly across its length. It also explains why similar electrical behavior can occur in systems with very different physical layouts, as long as the field structure remains comparable.
Thinking in terms of fields is less intuitive, but it aligns more closely with how nature behaves. Electricity becomes a dynamic pattern in space rather than a substance in motion, revealing a deeper and more accurate picture of a force that feels familiar but operates in ways that are far from obvious. A different way to explain electricity begins by shifting attention away from particles and toward interactions. In this view, electricity is not primarily about electrons traveling from one place to another. It is about electric and magnetic fields responding to changes and influencing each other. When a circuit is completed, these fields form and adjust across the entire system almost at once, creating a structured pattern that determines how energy moves. Energy, in this picture, travels through the space around conductors rather than inside them. The surrounding environment becomes part of the electrical system. Air, insulation, and even empty space play a role in guiding energy flow. This explains why the shape and layout of a circuit matter so much. Bends, spacing, and geometry affect how fields form, which in turn affects how efficiently energy is delivered. Wires take on a different meaning in this framework. Instead of acting as highways that carry power, they function more like boundaries that shape the fields around them. They provide a path for charges to adjust locally, allowing the fields to remain stable and directed. The real movement of energy happens in the structured space defined by these boundaries, not through the slow drift of electrons. This approach helps explain behaviors that seem strange under the traditional model. It clarifies why signals propagate faster than electron motion. It accounts for energy transfer in systems where particles barely move at all. It also makes sense of effects seen in high-frequency circuits where fields dominate behavior and particle-based explanations fail.
By focusing on interactions rather than objects, this view aligns better with both experimental results and mathematical descriptions. Electricity becomes less about things moving and more about relationships changing. This shift does not simplify the concept, but it makes the underlying behavior more consistent and easier to connect across different scales and technologies.
Physics struggles with electricity because no single model captures all of its behavior. Instead, several explanations exist side by side. In some situations, electricity is treated as moving charges. In others, it is described entirely through fields. At smaller scales, quantum ideas take over. Each model is accurate within its own limits, yet none can fully replace the others. This layered approach works in practice, but creates confusion when trying to form one clear picture.
The challenge becomes more obvious when moving between different conditions. A model that works well for household circuits may fail at high frequencies. An explanation that fits large systems may break down at the atomic level. Physicists switch between models depending on what they need to calculate, not because one is more real than the others, but because it is more useful in that context. This flexibility is powerful, but it also highlights the lack of a single intuitive explanation.
Because of this, mathematics often becomes the main tool for understanding. Equations describe electrical behavior with remarkable precision, even when the physical meaning is unclear. Calculations predict outcomes that experiments confirm, yet the underlying picture remains abstract. Many physicists can solve complex problems involving electricity while admitting they cannot easily explain what is happening in everyday language. Human intuition evolved to understand solid objects, visible motion, and direct cause and effect. Electricity does not fit neatly into those categories. Fields extend through space. Interactions happen without contact. Changes propagate faster than particles move. These features resist simple mental images, forcing intuition to give way to formal reasoning. As a result, electricity remains a topic where understanding often feels incomplete. The math succeeds where intuition fails. The models work without offering a unified story. Physics can predict electrical behavior with confidence, but explaining it in a way that feels fully satisfying remains an open challenge, even after generations of study. Got it? I'm ready to continue in the same style and flow. Send me the next section title, for example, Electricity at the Quantum Level, or Why This Matters Beyond Theory, and I'll write it with the same tone, structure, and rules until we reach the final conclusion. At the quantum level, electricity becomes even harder to describe. The clear boundaries used in classical physics begin to dissolve. Particles such as electrons no longer behave like tiny solid objects moving along defined paths. Instead, they act like waves spread across space, existing in many possible states at once. Their position and motion cannot be known precisely at the same time, only described in terms of probability. In this domain, electric fields also lose their clean structure. They fluctuate. They interact with particles in ways that are not fixed or continuous. The idea of a smooth field guiding energy from one point to another becomes less certain. Interactions happen in discrete exchanges rather than steady flows. Energy appears in small packets, released and absorbed in jumps rather than gradual changes. Does that effect also become harder to separate? Events do not unfold in a clear sequence where one action leads directly to a single outcome. Instead, multiple outcomes exist until an interaction forces a result. An electron responding to an electric field does not follow a predictable path. It follows a range of possibilities shaped by probability rather than certainty. This challenges the classical notion that electrical behavior can always be traced step by step. Concepts that work well at larger scales stop being reliable. Voltage, current, and resistance still exist, but their meanings change. They become average behaviors rather than precise descriptions of what individual particles are doing. The familiar images of circuits and flowing charge no longer apply in a straightforward way. At this level, electricity is best described through abstract mathematics rather than physical pictures. Equations capture relationships that cannot be visualized directly. The behavior remains consistent and testable, but it no longer fits into everyday logic. Classical ideas fade, replaced by a framework where uncertainty is not a flaw, but a fundamental part of how electricity operates at its smallest scales. These questions about electricity are not limited to theory. They affect how real systems are built and improved. Modern electronics rely on precise control of electrical behavior at very small scales. As components shrink, classical explanations become less reliable. Designers must account for field effects, quantum behavior, and unexpected interactions. Small misunderstandings can lead to inefficiency, heat loss, or failure. A deeper grasp of electricity directly influences how fast, stable, and powerful devices can become. Energy systems are also shaped by these limits. Power grids, renewable energy technologies, and storage systems depend on how electrical energy moves and transforms. Losses in transmission, unexpected interference, and instability often trace back to complex field interactions rather than simple resistance. Improving efficiency requires more than better materials. It requires understanding how electricity behaves in space, across distances, and under changing conditions. Future technologies push these challenges even further. Quantum computing, advanced sensors, and high-frequency communication systems operate in regimes where intuition breaks down completely. Engineers working in these areas rely heavily on abstract models because familiar concepts no longer apply. Progress slows when the underlying behavior cannot be explained clearly, even if it can be calculated. This places real limits on how quickly new technologies can move from theory to practice. These difficulties also shape how physics is taught. Simplified models are necessary for learning, but they can leave lasting misconceptions. Students often struggle when early explanations later turn out to be incomplete. Bridging the gap between useful models and deeper reality remains one of the hardest parts of science education. At a broader level, electricity exposes gaps in human understanding. It shows that mastery of equations does not always equal true comprehension. Even with centuries of study, one of the most essential forces in daily life still resists a single clear explanation, reminding us that knowledge often advances faster than understanding. Electricity sits at a strange place in human experience. It is one of the most familiar forces in daily life, yet it remains deeply mysterious. It surrounds us constantly, working silently in the background, rarely demanding attention unless something fails. Because it is so reliable,
It is easy to assume it is fully understood. That assumption turns out to be misleading.
Most people interact with electricity without thinking about what it truly is. Lights turn on, devices charge, signals travel across the world in fractions of a second. These outcomes feel ordinary, almost automatic, but beneath this smooth surface lies a system that defies simple explanation. The more closely electricity is examined, the more its behavior resists clear mental images. Simple explanations are useful, but they hide deeper questions. Electrons flowing through wires describe part of the story, not the whole. Fields guiding energy through space add another layer, yet still do not capture everything. At smaller scales, probability replaces certainty and familiar ideas begin to fail. Each explanation works only within boundaries, leaving gaps where intuition no longer applies. This creates a quiet tension in physics. Electricity can be predicted with incredible accuracy, yet its true nature remains fragmented across models and equations. Understanding how to use it came faster than understanding what it is. That gap has never fully closed. Instead, it has widened as technology advanced faster than intuition. Electricity reveals something important about science itself. Progress does not always lead to clarity. Sometimes it leads to better tools, sharper calculations, and deeper questions. A force can be essential, dependable, and powerful while still being conceptually incomplete. Even now, electricity remains an unfinished story. It continues to challenge how reality is described and understood. It reminds us that familiarity does not equal simplicity, and usefulness does not guarantee comprehension. One of nature's most dependable forces still holds unanswered questions, quietly operating at the center of modern life while resisting a single satisfying explanation. Electricity powers nearly everything around us, yet its true nature remains layered and unresolved. What feels simple on the surface is supported by hidden structures, shifting fields and rules that change with scale. Over time, science has learned how to use electricity with extraordinary precision, even while deeper understanding continues to evolve. That contrast is what makes it so fascinating. This journey shows that electricity is not just a tool, but a reminder of how complex reality can be. Familiar forces can still challenge the best minds. Clear results do not always come from clear explanations. And progress often reveals new questions instead of final answers. If this video helped you see electricity in a new way, take a moment to like it. It helps the channel grow and reach more curious minds. Subscribe to our channel for more deep dives into the science behind everyday forces. And stay with us as we continue exploring the mysteries that shape the world around us.